All right. Let's take a look at number one from the 4A handout. And in this problem, let's see, we're trying to graph root x, which is a parent function for square roots, and root x minus 3, which is really just a shifted version of the parent function. So let's start with the parent, y equals root x. And I'm going to make a little chart here. And now there are a few easy values to plug into a square root. The easiest one is one thing to note: you can't have negatives underneath that root, or else you get imaginary numbers, which you can't graph. So one of the things I'm going to say is we're going to restrict this. I'm going to put D for domain, so that I'm only using x values that are 0 or bigger. Okay. So that's called domain. That's whoops, sorry about that. That means the x's you're allowed to plug in, and in this case, it's 0 and bigger. So I'm going to start with 0, and the square root of 0 is just 0. The next easiest one to plug in would be 1, and the square root of 1 is just 1. And then 2 is not an easy square root because root 2 is not an easy number to evaluate. It's about 1.4 ish. Root 3, same deal, about 1.7, not a simple looking number. Root 4 is a nice number though, that's 2. So if x is 4, then y is root 4, which is 2. And then if you keep going till you get to the next nicest number to plug in, if you wanted to keep going, it would be 9, and the square root of 9 is 3. Okay, so that's enough to plot some points here. We got 0, 0. We've got 1, 1. We've got 4, 2. And we've got 9, comma 3 right about there. And if you connect those, you get a curve that kind of looks like this. And you can't quite tell. It looks like it flattens out, but it actually continues to go upwards forever. And so that you could keep going up higher and higher and higher, as far as up as you wanted to go, as long as you went far enough out on the x's. So this thing continues to go up forever, and you get every y value except negative y's. So that's linked to something called range, which is all the y's can be positive or 0. Um, it's okay if you're a little rusty with this stuff. We'll come back to it later on. But I'll mention it for now because that's part of the parent function, and that comes in handy anytime you do a transformation, figuring out what the domain and range are for those. Okay, so if we look at the other function, I'll use a different color for that. Notice the x got switched out for an x minus 3. And we've done a bunch of problems now, like, oh, if I start with y equals x squared and then I turn it into y equals x minus 3 squared. Or if I start with y equals absolute value of x, and then I turn it into y equals absolute value of x minus 3. Or what else have we done now? Y equals 1 over x. And then that gets switched to y equals 1 over x minus 3. This is the same sort of deal. I took y equals root x and I turned it into y equals root x minus 3. And in all of these cases, that minus 3 that you tacked onto the x does the same thing. It translates the graph 3 units to the right, which really means in your chart, you're going to add 3 to the x's. So then this will come out to be 3, 4, 7, and 12. And the y's never changed. Now down here, originally my domain was I could have 0 for an x and bigger. But if I'm going to add 3 to all my x's, well, my domain for this new function changes. It's now 3 and bigger. The range, though, the y values never went up or down. So this is still y is greater than or equal to 0 for the range. And now we can plot those points. 3, 0, which if you notice is exactly 3 units this way. And then 4, 1 is right here. And then the next one is 3 units over. That's 7, 2. And then 12, 3 would be up here somewhere. And then the new graph looks sort of like that. And so everything is exactly 3 units over. If you just slid the black one 3 units to the right, you get the red one. So this is y equals root x minus 3. And the black one, y equals root x. Okay, let's take a look at b. So b, the first chart's going to be the same because it's the parent function again. So 0, 0, 1, 1, 4, 2, 9, 3, if you want to go up to 9. I would say I want you to go up at least these 3, and then this one's optional. Okay. And now, let's see, this gets turned into x, and y equals root x, and now the minus 3 is on the outside. So that's sort of like the times that we did stuff like y equals x squared gets turned into y equals x squared, and then just tag on a 3 afterwards. And what that really does is it says, well, you had all your y's before, now they're the same, but 3 more. So it's a translation up 3, which really means, oh, sorry, not up 3. This is minus 3, my bad. So it's down 3. Sorry about that. Down 3. And so that really means subtract 3 from your y's. Okay, so the x's didn't change. It's 0, 1, 4, 9. But the y's all decreased by 3. So it's negative 3, negative 2, negative 1, 0. And if we go back and we think about domain and range again, for the original, the domain is x is 0 and bigger, and the range is y is 0 and bigger. And then if you think about what we did, we had to subtract 3 from the y's, but nothing to the x's. So the x's stay the same, but the y's are now greater than or equal to negative 3. And if we plot these points, here are the originals, 0, 0, 1, 1, 4, 2, 9, 3. That's the same as the black one in part A. And then the blue one, the one with the minus 3 at the end, is going to be 0, negative 3, 1, negative 2, 4, negative 1, and 9, 0. And if you think about what this one is, it's the same as the black one, but exactly 3 units down everywhere we go. So you can pick any point, go straight down 3 units, and you get the other point, its corresponding point. Okay.